This video is on antiderivatives and the indefinite integration. Up until now, we've been working with derivatives and all kinds of applications of derivatives, but we're going to change it up a little bit. We're now going to work with antiderivatives, or what's also known as integration. Now, if you look at this box that you have here, vocabulary and definitions, a function f of x is the antiderivative of a function f of x if the derivative of capital F of x is equal to the regular function f of x for all x in the domain of f. And this is just called antidifferentiation. The family of antiderivatives of a function f of x is the indefinite integral of f with respect to x and is denoted by the integral sign f of x dx. If capital F is any function such that its derivative is equal to an original function, then the integral of f of x dx is equal to f of x plus c is called the general solution, and c is called your constant of integration, which is just some arbitrarily constant. Now, you're thinking, what the heck does antiderivatives have to do with regular derivatives? Well, antiderivatives or integration is just the opposite of derivatives. You're now working in the opposite direction rather than in the direction we were originally going with. So if we look at example 1, it says antiderivatives differ only by a constant c. State three functions f of 1, f of 2, and f of 3 whose derivatives are f of x is equal to 2x. Well, if you can just think of three functions such that their derivative is 2x, you could think of plenty of them. So let's say we know that 2x is the derivative of x squared. So we could simply say x squared plus 5 would be one of the functions. Or x squared minus 7 could be another function. Or x squared plus pi could be another function. Because when you take the derivative of these three functions, they all give you the same derivative, being 2x. So now it says the expression, the integral of f of x dx, is read as the antiderivative of f with respect to x. So the differential dx serves to identify x as a variable of integration. The term indefinite integral is synonym for an antiderivative. We're not going to be calling them antiderivatives and indefinite integrals. We're just going to call them integrals, period. Example 2 gives you some notation for these antiderivatives. dy dx is equal to f of x. And simply taking dx together with our f of x so that our x variables are together, dy is equal to our f of x dx. And a general solution is given by this notation here that we have. So if we look on to the second page, you've got a formula of basic integration rules. And like I said, integration is the opposite of differentiation. Before, when we would take the derivative of a constant, we would say it was 0. So the opposite of that is saying, well, the integral of 0 is going to be some constant. Same thing with a linear function. Anytime we would have the derivative of, say, 5x, we would say the derivative was 5. Well, now the integral of a constant is now kx plus some constant. What I really want to get you to understand is this power rule here. You know that for derivatives, the power rule said you bring down the exponent and you subtract 1, and that's your derivative. Well, for integration, you're going to work backwards. First, you add to your exponent and you divide by that new exponent, and then add some c value to it. Make sure that you highlight all of this. Make sure that it's something that you have close by so that you can use it constantly. And then we also have integration for trig functions. Here are all the derivatives for the trig functions that I made you memorize at some point this semester. Don't forget them. They might come back in a pop quiz sometime this week. For the integration, well, the derivative of sine was cosine, so now the integral of cosine is going to be sine x, and of course plus some c. Now the reason that if you look at all of these integrals that we have here, they all have a plus c for them. The reason for that, they are called indefinite integrals because we don't have any boundary values. And we'll talk about those boundary values at some point this coming week. But for now, given that we don't have any boundary values, we include that plus c, which is that constant at the very end. We do have some transcendental functions at the very end, exponentials, bases other than e we haven't talked about yet, but we will get to before the semester is over with. Just wanted to give you some exposure to both the derivative and the integrals of those. And of course, here's ln of x and its integral. Now to do some examples. So applying basic rules, they want the integral of 3 to the x dx. Well, if we're going to use power rule, first we add to our exponent, which in this case is 1. So, and you add 1. Before you would subtract 1, now you're going to add 1. Well, 1 plus 1 will give us, we leave our constant of 3. So 1 plus 1 divided by this new exponent, which is 2. So then our final answer will be 3x squared plus, 3x squared over 2. Given that we don't have any boundaries, we have to include that plus c. Next example says, what is the integral of 8 dx? Well, there's no variable for me to add to, so I'm going to have to include a variable. So this one's just 8x plus c. If you look at this next example, just like we did with derivatives, we would take the first derivative, then we would take this derivative, and then this derivative. Same thing with integrals. For the very first part, x squared, we add 1, divide by that new exponent, so now we have x cubed over 3 minus, we add, using our power rule for integrals, 3x squared divided by 2 plus 4x plus c. And that would be it. Let's move on to another example. Rewriting before integrating. Just like we did with derivatives, anytime we had fractions or if we had radicals, we would send the exponents up, take the derivatives, and then simplify after that. We're going to do the same exact thing with integrals. So first we're going to rewrite it. So that'll be x to the negative third. Then we're going to integrate it. So we add 1 to that exponent, becomes x to the negative 2, divide by that new exponent, which is negative 2, and then simplify it. We don't want a negative exponent on the top, so we'll have negative 1 over 2x squared plus c. We rewrite square root of x to be x to the half. To integrate it, we're going to add 1. So it'll be x to the 3 halves divided by 3 halves. And then we simplify it to be 2/3 x to the 3 halves plus c. For this one, we've got a constant right in front of our trig function. The easiest way to rewrite that one is pull out the constant, leave everything else the same. Well, now the integral of sine is based off of our table is negative cosine. So we'll have 2 from our constant on the outside, negative cosine x. And then we rewrite it to send the negative to the front. So that's negative 2 cosine x plus c. Now it says, when integrating, think before you work. Practice will help you discover many tricks that make the integration rules fit your problems. Trick 1 says to rewrite, trick 2, multiply or distribute, trick 3 says to separate fractions. So let's look at the first one. The integral of 3x minus 1 squared dx, easiest way to do that is to first FOIL it out. So we'll have 3x minus 1 times 3x minus 1. When we FOIL this, we get 9x squared minus 6x